enough as it is without it being all garbled and everything too. All right. Anyway, you will have 20 multiple choice tests. Now, what I did was I loaded the chapters 15, 16, and 17 clicker questions on Blackboard. If you go through those, if you just put it on, there's nothing to do. You don't have to turn anything in. There's nothing to do. All you have to do is go to those, put it on view slideshow, and just walk through it. See if you can answer the questions, and then when you hit the next slide, it'll show you what the answer is. Then you go on to the next one, and your multiple choice questions are a lot like those. And they're all fastballs down the middle. I didn't pick any because they rate them like from 1 to 5, and I picked all 1s, 2s, and 3s. No 4s and 5s, nothing where, but if you had thought about it, if you had cubed this, then divided by the square root of, the resistivity, you would have got, It's all just real straightforward. So if you actually read, now I know the way 99.9% of us study science and math, what we do is we get the homework, we sit down, we read the first problem, then we start flipping through the chapter, right? That's exactly how we all do it. Now, what I want you to do is go through the clicker. Don't go through the clicker questions, but until you've read the chapter, just sit down calmly, without any, maybe with a highlight or something, and just read the chapters if you're getting ready to teach it to somebody, and then go to the clicker question and go, oh yeah, they said this, they said that, they said that, and you'll be just fine. And then the 4 problems I gave you, those are the 4 problems, okay? And you still get your 8.5 by 11 sheet. So if you go, we had a homework problem just like this one, could it show up on your notes? Maybe. Am I going to check? No. So there you go. The better you do, the less I have to grade. All right. So anyway, and it's only 7.5% of your grade. The most, like I said in the email, I'm killing you with the homework. The homework is hard, and you're slugging through it, and that's where you're really learning some stuff. And so, as you can see, I could pick any number of problems and make the test just impossible and flunk you all and say, y'all stupid, worthless, go on. But because this is how many is this the first time you've seen E&M, electricity and magnetism? First time, right? Yeah, stuff's hard. The stuff is hard. It's also very interesting if you relax and let yourself learn it instead of getting. And you guys are doing a good job. You really are. You really are. Okay, so that was what the point of that email was. All right. So if you go to your Blackboard, there on under the course content, you can find the clicker questions and just go through them. I mean, it's your own little practice thing, okay, to see what you learn from the chapters. If you know that is cold, you're going to fly through the first 20 questions, which is 60% of your test. Then you're going to have those 4 questions. I can't even remember what they are now, but it's yeah, just call it out. Anyway, all right, you're late, Natalie, but anyway, So there. I guess that's any other questions over the internet now. With my videos, I had a problem because they've only got like 5 of the lectures have been loaded so far out of the 9, and they're like, oh my, what are you doing to us? You lied. You said you're going to put it online. Well, were you all victims of the online experiment that I did once with Tess? No, you all weren't. Well, I did it once before. Power went out. Oh, it was just a nightmare. It was just a nightmare. I hated it. People's computers froze up, and I believed them, because, well, I mean, what are you going to say, Because it does happen, especially if I don't know if anybody still has, a few people still have dial-up and stuff like that. There is absolutely no way you can read Blackboard or any of these things if you still have dial-up. I mean, one question could take 3 or 4 days of it going through. And if something goes wrong at home, because every once in a while my little airport on my iMac decides it's not going to work that day because it's raining or something, So I just didn't want to do the online test. But that's their problem. But they're going to take the test next week on Tuesday. So, all right. So what we're going to do today So that you guys can, because how many of you have an orgo test on Friday? Killer Kilway sent me that email too. She goes, yeah, I'm giving an orgo test, but those that have class at 2 o'clock can come at 12:30 and all that kind of stuff. So you should come to class, but I'm not going to be here Friday. I'm going to give my mom a break and say, here, I'll watch Dad today. So anyway, because if we got the only class and I'll be grading this stuff. No class Friday. What's that? Going to see my sister? She comes here. She's the one with all the squirrel, not me. She's the investment banker. I'm the teacher. All right. Anyway, so here we go. So what we're going to do today? I bought a book, but I got it close. What we're going to do today, so you can be relaxed, you stay for your orgo, you get your homework done, is I want to look at that one problem that seems to be causing people's, where you got electron volts and all that kind of stuff, and you got to figure out the energy, because you're going to have a test question kind of like that, but at least you're going to get the stuff in joules. Now, remember the big idea, energy, U equals Q times V. Equals Q times V. Now, we got to figure out what the heck an electron volt is. An electron volt is real simple. Take an electron, multiply by 1. That's an electron volt. Okay, now that is not a joule. Okay, but it is a Q times V. So to get the joules, you take that 1 electron volt and divide it by 1.6 times. You divide it by the electrons, and guess what you're left with? You're left with joules because you got volts per coulomb, which is a joule. Okay? Y'all are confused by that. I got the what? Volts per coulomb gives, no. Coulomb volts. Coulomb volts gives you joules. Sorry. You're right. I was making that up. All right, so anyway, so let's look at that one problem. And I've got good old Mastering Physics here. And then, you know what we're going to do? We're going to fly through between now. We're going to see how many homework problems we can get done on Chapter 17. Okay? Because that's the way you're going to learn it. We're just going to work it together. Because it took me a minute to do those homework problems too. A few of them, and one of the problems was, anybody got a calculator out handy? Everybody got a calculator out and it's handy? Take 2.6 and divide it by, 1.2. What'd you get? 2.16, right. I put that answer in like 15 times on Mastering Physics. Wrong. The answer's 2.3. You know, we're going to scrap now because it's not. That's not what it is at all. All right? So I understand sometimes you guys go, I put in the right answer. And I'm usually like, yeah, right. I know I did. Well, 9 times out of 10, you probably didn't. But sometimes it was wrong, because then I said, all right, I just asked for the answer, they put it in, I said, well, you're wrong. And so, have you ever noticed that when you finish a problem, you can rework it for practice? So I reworked it for practice, they give you new numbers. And I did the new numbers, and I did it right. So I'm like, okay, loser. But
answers with negative exponents, I get all of those wrong. So
what are you doing?
exactly, that's what I want to know.
Negative exponents?
Yeah, negative exponents, they count it wrong, and then you show me my answer, and you show me that answer, my answer's the same. So the
Okay.
But then below it, she said it's not the negative answer, it's the positive answer.
Okay. All right, let's go to assignments here. Courses. What course are you? We're 220A. Let's go to 16, which is past due. Uh-oh. Is this the one that's rough, 1630? Yeah. All right. Okay, y'all recognize this guy? Y'all hate him by now? Yeah. All right, now. Here you go. It says this. It says calculate the voltage required, all right, to accelerate a beam of protons. When they talk about a beam of protons, we're talking about one proton at a time. Go bing, bing, bing. Okay? So you should be thinking, all right, what I want you to do on your cheat sheet, though, make sure, because that might not be on the test, I might forget to put it on there. I will tell you if you get stuck, but make sure you put on there the mass of a proton, mass of an electron, charge of an electron, charge of a proton, which is the same magnitude-wise. One's is positive, one's negative, but their masses are very different. Electron volts. You know what the answer to this one is? If you're used to using electron volts, you come down and you go, oh, 5.1. Boom. Ha! Calculate the voltage required to, because the charge, all right, now, you might be going, well, wait a second. Wait a second, how did you get that? Because what I did was, here's the, as I say sometimes, here's the deal. All right. And I brought a size 10 pin for this, for this, okay? So I'm thinking about you guys all the time. Yeah, trying, how can I make this, how can we go slower and louder? Because this stuff is hard. All right, so here's the deal. If I've got 5.1, this is supposed to be fatter. Oh, let's zoom in. That'll work, except for my hands are ugly, but other than that, that's all right. Let's zoom in. Boom. There we go. 5.1 electron volts. If I divide that by 1.6 times 10 to the times 10 to the negative 19, I get joules. This will give me joules. This will give me how many joules it is. Okay? And then, all right, so this gives me the joules. So this is joules. All right, Bob, so what's your point? Here's my point, is that we found out that Q times V equals joules. So basically, if I take that 5.1 electron volts, oh wait, is that right? Or do I multiply? Oh my goodness, I made a mistake. Golly darn. I've got to take this 5.1 electron volts, okay, because this is telling me I've got 5.1 electrons. It's 5.1 electrons. Charge times volts gives me joules. So if I've got 5.1 electrons, how much charge is that? 5.1, I've got to multiply this by 1.6 times 10 to the negative 19. Okay, coulombs. All right, and so that's 5.1 times 10. So that gives me my electron volts. Now, this gives me joules. So if I've got Q times V equals 1.6 times 10 to the negative 19 coulombs times 5.1 EV, okay? Now, if I divide that by the coulombs, how much charge is in 1 coulomb? 1.6 times 10 to the negative 19. So if I divide that out, so if I divide this by Q, I get 1.6 times 10 to the negative 19 coulombs. That goes away, and I'm left with 5.1 volts. Okay? Because this E actually went away because we put it over here. All right? Okay. So that's what they're saying on that problem. All right? Now then, I found out something because I was actually reading and I was picking out test questions to give you out multiple choice questions. And I didn't know this. I've been saying something wrong for 10 semesters or something like that when I'm teaching this class. We can have something less than, this is just for your own general knowledge, we can have something less than 10 to the negative 19 coulomb, 1.6 times 10 to the negative 19 coulombs. You know what it's called? A quark. They're the things that build electrons and protons. Okay? And then, so they've got charge that's even smaller, and then we got things called gluons that have smaller charge and all that kind of stuff. But anyway, see, physics doesn't get interesting until we just bore you to death, and then it gets kind of cool. But anyway, all right, you got to go through a lot of blocks and sliding pulleys and things like that before we get to the good stuff. Okay, let's go back to the computer. So we got that one. Calculate the speed. Oh my goodness. You're going to have to do this on the test. We already know that. But on the test, you're going to be given what the charge is, probably, or what the joules are, how much energy is there in joules, Okay? And you know that QV equals the joules, and calculate the speed they have if they have that kinetic energy. All right, first of all, I've got to change this thing to joules. So, in other words, I've got to change this. I've got to go, 1.6 times 10 to the negative 19. Oh, you can't see what the heck I'm doing. I'm sorry. I do that to you all the time. It's kind of neat up here. You can really, let's do a new problem. Calculate the speed, because this is important. You're going to do this on Wednesday. Speed. Okay. And I can't remember what the questions, the way the questions were, but let's just take a look at this 5.1 electron volts. That's an energy ray because I've got 5.1 electrons times 1 volt. Okay, so that's actually kind of a Q times V, but it's buried in there. It's given an EV. The joules of this would be 1.6 times 10 to the negative 19, which is the charge on electron, times 5.1 times 1.0 volts, which is what they mean by that. Okay, and that gives me my joules, or my U. You guys have seen a lot of this U stuff. All right, so if U equals 1/2 mv squared. There we go. That's how we have to do this. You got to convert it to joules before you can find the velocity. All right, so it'll be 2U over m, the square root of that, equals V. Now, a real fun thing to do, and Dr. Stoddard made us do this, actually in Physics 460. She said it was like 3 points on a test. She said, all right, you guys can do it. This was actually kind of one of our questions. It's like, oh, this is a 220 type question. Yeah. But then she said, and this could also be a 220 question. I'm not going to do it to you, but show why this is equal to meters per second. Wow. How do you get from electron volts to meters per second? By dividing by kilograms? It works. It works. But if you just stick with joules and you know that force times distance, you can get meters per second because you're going, oh, joules are force times distance. That's MA. Divide by M, I'm left with A. And I take the, I got distance squared over second squared. Hey. That's not too bad. I take square root and get meters per second. Yeah?
The first part, the U equals 1/2 mv squared.
Uh-huh.
The M the mass.
Yes, because that's good old kinetic energy.
Is the mass the 1.6?
Oh, mass. What's the mass of a proton? 1.67 times what?
10 to the negative 27.
All right. Might be able to win a bar bet with that someday if you got to memorize. Free fat tire. What? Yeah. Yep. Divided by the mass, multiplied by 2, divided by the mass. Okay, and that should work. All right. I'm not going to plug it in because it might be wrong. No, it'll be right. I don't. Okay, so that's the way you'd find that V. Okay. Now then, it says calculate the voltage on part C. It says calculate the voltage required. Ooh, KeV. What's KeV mean? Kilo electron volts. Right. That's 1,000 of those things. That's 1,000 of the EVs. So that might have been where you had a little bit of problem. That is 2,700 electron volts. Okay? And so you got to do the same thing. So the voltage here should be what? Oh, let's see. This will be exciting. My palms are sweating. I'm so excited about this. Here we go. 2,700 volts. Is it right? Yes! I love it when a plan comes together. Okay. Cool. Cool, cool, cool. All right. So again, calculate the speed. Uh-oh. We got to go through that thing. When you give an electron volts, how do you find the joules? What? Multiply it by the 1.6. Multiply it by the charge of an electron. Okay? And that will give it to you in joules. Because 1 electron volt equals 1.6 times 10 to the negative 19 joules. Okay? All right, and then we go through. Oh, this one. Oh. What about this last one here, part E? Yeah, D will be the same thing as part B, except now it's much bigger. It's a much bigger voltage. So your Q times your V is now 1,000 times bigger, or 500 times bigger in this case. So I wonder if it would be something as easy if we found V and multiplied it by 500, it'd probably come out to be the same thing, or real close. They'd say getting close. I like their little obnoxious thing. You're so close. It's right. I get that. See, I do the homework too, so I know you're frustrated. I feel your pain, kind of, except that I'm not getting graded for it. All right, calculate the voltage. So, this is pretty easy. All right, so what would we do for this? If we're given the joules, how would we find the voltage? Divide by Q. Right, divide by that 1.6 times 10 to the negative 19. I get stuck. My brain, it's negative 19. So if I just take that 3.5, okay, I'm going to do it because, oh no, I'll wind up with a 1,000 volt thing. Because I get 3.5 e to the negative 16. Oh, we got to get going. All right, the rest of it's just the same. 1.6. We got to get started on chapter 17 stuff. Okay. All right. So there's that one for the most part. That's all right. Now let's go and find some more assignments. This is not due till Friday. What? Yeah, 17 will be on the test. Yep. But 17 boils down to this. V. There's the. All right. Here are the. What time is it? Oh my gosh, we only got 20 minutes. Y'all can look up the equations for what this is, because let's go through this. All right. On this one, all right, hold on a second. Let me do this for you. One of my alert students taught me how to do this so everything shows up on one page. All right, so here we go. Now, it says when the switch in the figure is open, all right, when there's no when we don't feel this resistance at all, the voltage reads 3.1. Okay? In other words, the whole thing here reads 3.1. All right? When we close the switch, the voltmeter reads 2.92. So that means that there's that internal resistance or a back EMF that we talk about in this thing. And so when that happens, so it says find the EMF E. In other words, it's this 3.1. All right, it's this 3.1 because it's the voltage. It's the voltage right here before we close that switch. All right. Okay. There it is. So that the 2 meters are ideal. All right. They're ideal meters. In other words, they don't have an internal voltage that are taking it away. And have you guys started doing circuits yet in the lab where you're doing the voltmeter? You're trying to find that internal resistance inside the voltmeter because you're taking all these measurements. Yeah, that gets kind of tricky. All right. So this should just be 3.1. What did I say? What's the second part of the question? 3.1. I shouldn't spend too much time on this because you guys can figure this stuff out. Okay. Find the internal resistance of the battery. Here it is. V equals IR. Find the internal resistance of the battery. V equals IR. So, here's I, 1.67 amps. And the total voltage of, what is that going to look like? I think we subtract those two. We subtract 3.1 minus 2.92 0.92. That gives you your back EMF in there times 1.67. So you can find that internal resistance there. So you get a small voltage. You get 1.67. I think. Solution view. That's always a good view to do. There we go. 3.1. There we go. You subtract the 2 for that one and divide by I that they give you. I wanted to make sure. I didn't want to send you off on a wild goose chase. Okay, then when you close the switch, what you do is you take that second voltage they give you, and it's going to be 2.2. All right, there we go. And then the last one, yeah, the resistance of that one resistor is just that V2 divided by I, which is your second voltage. All right, so that's good. Okay. Let's move on. Okay. Oh, this is kind of a cool problem. I'm just going to kind of explain to you how to do it real fast. Current. Notice we've got, you guys are used to chemistry. You got these, basically we got salt, right? You got NaCl, isn't that salt? Last time I remember. Okay. And it doesn't matter, current, I know we beat you up with vectors and all this stuff and where they're going and everything else. Current doesn't make any difference. It's just got to be moving. We don't care. So the total amperage, so you're going to take, this is a charge, right? And remember, it's charge per second. So you're going to find the amperage here, you're going to, if this is the number of protons, what are you going to do with that? Multiply it by the charge of a proton, right? That'll give you your charge of the proton divided by seconds. This is your charge of your electrons. Now you're going to treat this all quantitatively. Don't go, oh, well, these are positive and these are negative, so I should subtract them. No, they're flowing in there. So you just add them all up. You add them up. And it should come out to be around 10 or something like that, 10 milliamps. And always check over here for your answer. You're going to get amperage. If they want it in milliamps, multiply it by 10 to the third. Okay? And that'll give you your milliamps. All right. Good. Good. Okay, what is the direction of the current? All right, currents now. We're going to go the traditional way we do it. This is going to be embarrassing. I'm going to pick this one. And then, oh, good. Ha! Just remember it's toward the negative when you get there. All right? Because we're going to use because the way we do currents in circuits is we have the protons moving. All right. Okay, this one. Oh, this one's kind of a fun one. This is all about resistance, okay? This one is all about resistance. If the thing is coming through the wire, and they kind of beat you up on this formula a lot. Remember this, that resistance R equals the resistivity, rho, that's not density. That is not density. It's resistivity of the thing divided by L times over A. That's what the resistance equals, and they give you a lot of problems where you just mess with the algebra of that. Okay? Like if I double the length and I leave the A the same, what happens? To the resist. So if I double the length, what happens? Yeah, it's going to go. The resistance is going to go twice as high, right? In other words, it's going to take a lot more. And resistance is this. How much voltage do I need to push charge through it? The thing. So the resistivity of a piece of wood is really, really high. It takes a heck of a lot of voltage. It takes a bolt of lightning to burn that wood, all right, to get the electrons to go through it. All right, and there's a lot of energy. Okay? All right, with copper, not so much. With aluminum, even less. That really flows. So that's what those problems are all about. They're hitting on those, and it's kind of a fun little drag and drop thing. Don't be confused by this. I missed it, of course, the first time because this face and this face, these two guys are not equal. or this one and this one are not the same. X and Y are not the same. All right? For some reason, I thought they were. I don't know why. Or I thought X and Z were the same. That's what I thought. X and Z were the same. They're not. Because Z is 3 times 10 is its face, and length would be 4, and X is 4 times 10 is its area. So it's going to be less than Z. Okay. So y'all can, so based on this formula, that you can solve those without much trouble. All right. 4. One of these is really nasty. I mean, like really nasty. Oh, okay. This one's fine. Made from 2. Okay. I'll just tell you this. There are 3 answers here. You got to check all 3, and you guess which one out of those 3. Now, if they're the same one, if they're the same material, which one doesn't apply? No. No. Okay, you guys got some work to do. Okay, good. Here we go. All right. Now look. What is this? This rho is your resistivity, right? And it's dependent upon what? The material. So if it says 2 copper wires, this guy never changes. Okay? But if this changes and this changes, and also depending upon if the resistance changes, that's going to cause more current or less current to flow. All right? So 3 out of those 4 will be your correct answer. All right, let's keep going. Ooh, difficulty 3, I don't like that. Should only take you 4 minutes. All right, anyway. All right. Oh, a wire of length I is across it. Okay, now this one is where they stretch the wire. So we're going to go to this formula right here. Now remember, the density is going to stay the same. So if I stretch the wire, what happens to its area? It decreases. It decreases. So what you're going to have to do on this problem, all right, what you're going to have to do on this problem is this. And I have to work it out real carefully each time. I've got to go, okay, my original resistance is this. This is my original, is L over A. And my stretched resistance is going to be rho times 2L over the cross-sectional area. Now remember, the volume of the thing stays the same. So our differs. Rho V equals the mass. I worked all this out earlier. So, and this is density. I'm sorry. Now, this is my density. Okay? But anyway, if the volume of the thing is length times width times height, okay, and I want to keep the volume the same. In other words, the density is going to stay the same, so I got to keep the volume the same. If I want to keep the volume the same, but I double this times width, what am I going to have to do? Half the height. So my area comes out to be 1/2 the area for it to work out to be the same. Then you got a little algebra to do here, so be careful. Yeah, you got a little algebra to do, so be careful. Right. Yeah, it comes out to be 4L. Right. So that, yeah. Okay. So when it says make it in terms of R, you'd say something like 4R. Hopefully that's right. Yeah. Okay. Now, be careful. Yours might say we stretch it to 3 times. If we stretch it 3 times, what would we do? Might even be 9R in that case, right? Okay. This isn't too bad. This goes to the standard equation, V equals IR. Okay? Oh, except it's asking for power, Bob. So tell them what power is. Power is equal to this. Yep. Power is equal to IV. Or, since V equals IR, How are we doing for time? Not bad. So if V equals IR, then we've got R can also equal V over I, or R equals V over I. So what does that do for me? Nothing. Or I can say I equals V over R. That's what I was after. And so power can also equal V squared over R, or power can equal I squared R. Three ways to say it. Okay? And so everything on this problem is just a combination of that. All right? And so what is the power dissipated throughout the circuit? Okay? So what do we need to find? Oh, they add a second resistor to the thing. So we start off with this, then we add a second resistor so it looks like that. All right? Now, resistors in series. They didn't tell you this. This kind of aggravated me a little bit. Resistors in series are not like capacitors. You just add them if they're in series. Okay? You just add the resistors if they're in series. So now all of a sudden we've got P equals, oh yeah, we're supposed to use V squared over R. So P equals V squared over 2R. That's my new one. Oh, yeah, you can't see that. Sorry. There we go. P squared now for my new one equals V squared over 2R, which is half of what the old one was. All right.
Why is it 2R?
What?
Why is it 2R?
Because we added another resistor right here. You'll see when you go to the problem. And then, guess what they do? They put them in parallel. All right? So resistance in series equals this, R plus R. You can't see again. Okay? Resistance in parallel, 1 over RP equals 1 over R plus 1 over R. Okay? So it's just the opposite of the capacitor things that you did. Right? Now, I don't ask you any of these kinds of questions on the exam. In fact, I told you what the chapter 17 is. Just regular straight P. Oh, the chapter 17. Enough of this messing around. Here you go. Let's do something that's good for you here in the last. Make sure that we at least get to this one. This one looks ugly. Oh, it's not ugly. It's not bad. We'll get to it in a minute. We'll come back to this one because it's kind of fun to do. And remember, when power equals IV, okay, or power equals V squared over R. All right. So if I know the voltage, power equals V squared over R is going through that thing. All right. But I don't know what the drop voltage is, so I've got to figure out the current that's actually flowing through here would be V equals IR. So I got to know what the current is, so that because the voltage going through there is going to be a little bit different. But anyway, but if I take power and multiply it by time, what do I get? If I take power and multiply it by time, what do I get? What physical entity? Work. Or work is also what? Energy. Right. Work and energy. Same thing. Okay. So yeah, because we're doing work to get those electrons across that resistor. All right. So we're doing a lot of work to get those electrons across that resistor. So it equals energy, and so if that's going to heat up, so that's how we get the heat. And remember, Q equals M times C times delta T from chemistry when you're trying to raise the heat of something. How many joules do you need? That's what they're doing here. So you find out the power, you multiply it by the time, and that equals the MC times delta T for that. But we'll get to that, and we'll come back to that one. Here at the end. It's hot in here. Here it is. Is this one? No. That one's pretty close. Yeah. This is what your test looks like. This is what your test looks like. This is pretty good. This isn't bad. Okay. This is problem number 8. All right. So it says a 1500 watt water heater is designed to be plugged into 120 watt, into one of these guys, 120 volts. All right. Now you got to figure out the amperage that it's going to use. Okay, and so if P equals IV, pretty straightforward. P equals IV, so what do? Take the power divided by the voltage. Get amperage. Resistance, V squared over R equals the power. So they give you the voltage. So you take P equals V squared over R, and so you take V squared over P, and you get the resistance. Those are that's kind of nice and straightforward. In fact, let's move on, because I don't think your test question is that easy. Almost. Oh, this is a good question. This is a good question. To move 3 coulombs of charge from one electrode to another in a 12-volt battery, you must do how much work? Volts isn't work. What's work? Joules. How do I get joules with volts and coulombs? Charge times voltage gives me my energy. So it's good old QV. So that should be 36 joules. Now, this is what I don't like about multiple choice tests, if it's a test question, is in the heat of battle, it's real easy to pick 36 watts just without thinking about it. Completely wrong. You don't know what you're talking. No, I know it's joules. So that's why I like. So be careful on your multiple choice, okay? Be careful. You'll have plenty of time. We'll have 5 minutes. Okay. Oh, this one's kind of nice, and basically what you do is the first time you add them up, and then on the second one, for the minimum, for the maximum, you just add them up. You know, if you put, in other words, if I had 3 8-volt batteries and stacked them end to end, how many volts would I have? If I had 3 8-volt batteries and stacked them end to end, how many volts now do I have? 24, right. There you go. And then the minimum number of voltages I could have from that would be 16. Yeah. But this one, what do you think the minimum voltage is you can have on this one?
730.
I'm waiting for someone to say 4. Because, remember, voltage pushes charge. So if I have one guy pushing 12, and one guy pushing 7 back, and one guy pushing one back, how many total voltage pushing is going? 4. Yeah, so you take the highest one and subtract your 2 little ones. Boy, I hope that's right. 20. See if that's right. Submit. If it's wrong, we'll quit. Okay, there we go. Cooking with gas. Now, the rest of them are pretty easy. Uh-oh. Oh, my gosh. Milliamps, proton, hits a current, hits the target. Okay, so you got a proton, you got amperage, and you got a proton. All right? So, how many protons? Well, can you figure out your charge here? If you know your amperage, and you know it's per second, remember amperage, I is charge per second, so you should be able to figure out the charge, and then you can figure out from the charge, you can figure out the number of protons, right? Because you take that charge and you divide it by the charge of a proton. So you're on your way. Ooh! This thing gave me fits, I'll be honest. I was going, you're making me mad. All right, 25 megavolts, electron volts. That's 25 times 10 to the 6th. Okay? 25 times 10 to the 6th. That's how much energy it has. All right? Basically, what did you do here? Oh! Yeah, joules per second. So basically what you do is you take your K. You got to figure out your K. Which is your kinetic energy. But anyway, you take this guy and you multiply it by this guy, and it works. I'll just tell you that, because it was driving me crazy. It was making me mad. All right, so you take 25 times 10 to the 6th multiplied by 9.2 times 10 to the negative 3. Don't ask me why, it just does, okay? And we'll talk more about these on, oh, why don't we do this? Why don't we do this? All right, we're about done. In fact, we've got to end here. Okay, so I gave you the email what the test is going to be like. Now, hold on a second. Let's go here. So, yeah, let's make this like do edit. Let's do it. Let's make it do for like Tuesday so that we can talk about it.
Can you give us one more day on 16? Yeah, that was great.
One more day on 16. Oh, quit crying, because some people have already got it. All right, so here we go.
Do it the old rusty way.
There you go. All right, so that way we've got chapter 17 now due on Tuesday, since we're not going to meet on Friday. So that way, if you got any other questions from the homework on 17, you can do it then. All right. Now, I'll have office hours from now until